excuse me. One thing worth looking at is this particular simulation. Okay, I'm going to try to pull it up here. Again, it's from the FET website. I'm hoping it is opening up right now. Okay. I'm going to try to reduce it a little bit. Okay, this simulation right now is showing a lot more than what I want. It's going to allow us to view position, velocity, and acceleration. And since we don't know much about the others right now, I'm going to just close them up and have only position. Okay, and now I'm going to extend this a little bit. Okay, and now what we have a person here, and it tells us we can drag that person. And as we drag the person, we can see the position versus time graph. Now, for example, what I'm going to do, I'm going to move the person from this position here, where he is at the origin at 0 meters. I'm going to move him from 0 meters towards the tree, but I'm going to stop at -6 meters. And I'm going to let him stay there for a little bit, then move towards the house and stop at 4 meters. And then I'm going to move back to the 0 meters. Okay, let's try to do that. But before doing that, try to think of how the graph is going to look like. So, since we are starting at 0 meters, we should start at the origin. And it's going to move towards the -6. So we are going to move below the x-axis. And then, when the person is going to be at rest at -6 meters, it should be a horizontal line at the -6 meters. And then we move forward towards the 4 meters, and then it will be horizontal at the 4 meters. And then back. Okay, let's try that out. Okay. Okay, now that's the end. Okay, of course my hands were a little shaky here. We started at the origin and we moved back towards the -6, as I mentioned. And you notice here when we are at rest, when the person does not move, it's a straight horizontal line at -6. And then we moved forward towards the 4 meter. Again, it's shaky. My apologies for that, but so it means that here the person momentarily stopped and then stayed at the 4 meters for a while and then moved back to the 0 meters and stayed there. Okay, one good thing about the simulation is we can rewind and view the motion again. Okay, so here at rest and then moved back, slowly stopped, moved back, and then stayed at rest there for a while. Okay, now in a little bit, at t equals 6 seconds, start moving back a little faster actually, stop there momentarily and then move towards the 4 meters. Okay, and stay there at rest. Okay, there is a slight jerk there that's accounted for. And look how fast I moved toward the 0 meters. And then here at rest at 0 meters. Okay. Now this shows us an example. Let's try to show another example. I'm clearing the graph. Okay, now in this particular case, what I'm going to do, I'm going to move him towards the house, and then back, and then forward again. Okay, towards the house, I'm going to move him slowly. Okay, he's at rest there. Now here, I'm going to try to move faster. Slowly, faster, fast, slowly. And I'm going to stop there. Okay, now let's observe a few things here. Okay, I'm going to rewind and play back. Okay, now the person is moving slowly, momentarily stops, and again moving slowly, and then stops at about 6 point something meters. Stays there for a while. Now this whole time right now, the person is in a positive direction relative to the origin. Notice here how when he moved back very fast. Now he's moving forward slowly. He's at rest, moving back very fast, but then in this case he moved back to the negative territory relative to the reference. And here he's moving forward fast, and he's moving back slowly. And he's at rest here. Again, from a graph position versus time, we can determine the position at any time. If I tell you where was he at t equal 10 seconds, we are going to come here and look at 10 seconds. 10 seconds is at about here. So at about 2.5 meters, plus 2.5 meters. Where was he at 13 seconds? 13 seconds is here. That's at about minus 2 meters. So we can figure out the position at any time by just reading it off directly. And again, we can get the displacement by getting two positions and getting the difference. One last thing, we'll get back to this later on. Notice the difference in the shape of the graph when he's moving slowly or fast. In this case, he was moving slowly, slowly, faster, 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 and slowly. Now, you see it's steeper when he's moving faster. We'll get back to this when we talk about velocity. Hopefully that will make sense then. Now, since we talked about position and displacement, it's time to discuss distance. Distance is what we use usually in our common day life. We talk about moving distances, we don't talk usually about displacements and positions. In physics, a distance is not a vector. Direction is not important. Now, what makes a distance different from a displacement is the fact that a distance is an overall length. It depends on the actual total motion. It depends on the way the motion happens. For example, if I have a person, let's get the pen working again first. If I have a person starting here and moving along this path to arrive to this new position here. So this is position 1, this is position 2. The displacement would be the straight line path from position 1 to position 2. That would be my displacement. The distance traveled, however, is going to be the length of this curve, the overall length. Now, there are cases where the magnitude of the displacement is the same as the magnitude of the distance. That's if the motion is along a straight line. But in most cases, they are different. Let's take a couple of examples. We have a racehorse that runs 1500 meter full circle in a racetrack. What is the displacement? So this is my racetrack. The horse starts here and ends here. Initial position here, final position is here. So what's my displacement? My displacement is going to be 0, since the initial and final positions are the same. What would be the distance traveled as the horse goes around the full circle? The distance traveled is the circumference of the circle that's given here as 1500 meters.